Just for the delay in posting these, and it's mainly because of the some of the issues with uploading big files, and it doesn't allow me to upload big files from slow internet connections. And so what I'm going to do is to upload them to a YouTube channel that I will give you access to, so you can open up these and play it on a regular uh, internet connection rather than download it and things like that. So I've been trying to do that. I hope I can do this successfully. Anyway, this is lecture 4. Um, and we are going to talk about um, the processing of polymer composites and how the processing methods can correlate to the properties of these composites, and what kind of properties are required, especially from a matrix standpoint, for improving the bonding between the matrix and the fibers. Because in polymer composites, the most important aspect is the um, the bonding between the matrix and the fiber. So in order to get that, you have to have a property called the fibers have to be vetted out as well as possible with the matrix. And the other thing that we will talk about in this class is the effect of additives. What kind of um additives are usually found in polymer composites, especially from a filler pigment. So, you can have different kinds of colors and things like that. What kind of control agents are required for controlling the viscosity of the matrix, and what kind of surface agents are required from the improving the bonding between the matrix and the fibers. So, this is a list of different composite material technologies. Uh, I've talked about it briefly in some of the previous lectures, and there is information about the different kinds of reinforcement fibers, typical uh, filler content, resin matrix, and things like that. So you can just take a look at that, and it will give you the different kinds of processing and fabrication methods. This is quite a bit of information, but it tells you everything about the different kinds of composite systems, including what kind of economic considerations are required from a market perspective. So it should tell you all that. Okay, and the other thing, especially from a military perspective, is what kind of data is available um, for design engineers. And all of these design properties have been put together in what is called the Composite Materials Handbook, and they call it Composite Materials Handbook 17. And it is available actually on at a website, but I think I have that, and I will upload that into the content sometime very soon. And this contains the information pertaining to all three major types of composites: polymeric, ceramic, and metal matrix composites. And there are also roadmaps that have been established for the use of this handbook and how to use the data in it. So if you Google the name itself, you might be able to get free access to the different volumes. Okay, so these are the different roadmaps in the mill handbook. So military handbook 17, and the current one is revision F, volumes 1 to 3, and there are different roadmaps that you will find in this book, and each of those roadmaps relate to particular sections and topics for use of composites engineers and design engineers. So we will continue the discussion about different kinds of polymer matrices, and here the what I want you to learn in this part of this lecture is about the effect of different kinds of solvents, because you're going to be using these composites in different kinds of applications, and one of the major applications is to use them as containers, big containers. So you can they are supposed to have um, re, um, pretty good corrosion resistance, but still some of those composites might have issues with regarding different kinds of solvents, especially highly aromatic solvents. And but you will see that some of the thermoplastics, especially for high performance applications like polyaryl ether ketone, or they call it PEEK, are extremely solvent resistant. But there are some types of polymer matrices that are not very good, that do not have very good resistance to solvents. Mainly the resistance of these composites is due to the compact polymeric packing. And but uh, if the molecules are aromatic in nature, they have extremely good stability. But if they are not, they are not going to stand, and they become very um, I would say that the molecules can penetrate between the fiber layers and attack the fiber matrix bonding. Uh, and the reason for me to bring it up is because one of the biggest markets for composites is in handling of different kinds of fluids. It is used in pulp and paper manufacturing. It is used in oil and gas transport and refining. It's used in chemical processing, wastewater treatment, composite pipes, fittings, etc. And most of these resins can be categorized in different ways as far as their chemical resistance is concerned. And it's discussed in terms of the degree of chemical attack that they can withstand. Many of the resins can reasonably withstand the different kinds of resins, different kinds of solvents, but some of them do not. And but depending upon the application, suppose um, the fluid that you are going to be transporting is extremely reactive, then you have to use very high cost and premium resins. So you need special resins with specific resistance. And you need also that these composites have to be qualified through special tests. For example, in the case of transporting compressed natural gas and cryogenic fluids, since these are going to be they are going to be on the road, they have to pass what is called the Federal Motor Vehicle Safety Standard 304. So they have to pass specific tests, and without that you are not even allowed to sell these materials in the marketplace. You also have, for example, if you have a specific type of resin, what you might do is you might paint them just like you would paint or you would galvanize the different kinds of steels. So you can have some kind of a staining agent, and they will interact with the polymer, and they would create a permanent stain. And some of these staining agents are polar. So if your matrix is a polar type of a matrix, then you need a polar type of a staining agent. As I said to you, if these are going to be used for transporting gases like liquid oxygen or gaseous oxygen and things like that. You do not want those gases to be diffusing between the fabric layers. Or if you have very small molecules like helium or hydrogen, you have to have some kind of an uh, agent to the matrix itself, so that those matrices are not going to be reactant towards the composite material or the composite matrix itself. And if you are going to be using oxygen, you can add antioxidants. And these antioxidants, you don't need to add a whole lot. It's just 1 to 2%. If your gaseous molecules are extremely small, then they would tend to seep very easily and go through the composite matrix itself. So you have to have specific type of testing. For example, you need to evaluate what is called the barrier property. So you would put it into a system where you have a gas on one side and you measure the amount of gas that is leaking through the composite over a period of time under different conditions. It could be under cryogenic conditions, it could be under heat or moisture and things like that. And especially if the service conditions can cause some kind of a swelling of the polymer, then it can increase the polymer gas interaction. So as I said to you, if the gaseous molecule is extremely tiny or small, then it can increase the permeability of your composite. If you have more cross-linking, if you have more higher crystallinity, then it will reduce the permeability of the composite material itself. The other property that you would find, especially in transportation type of applications, you have to have good resistance towards fire and burning. And that's because some of these types of polymers burn readily, and even if they do not burn readily, it might give up noxious fumes. So the noxious fumes are also not going to be an extremely good thing. So if your matrix polymer is aliphatic in nature, they would burn very readily. If they are aromatic in nature, they burn very slowly. They also create what is called char, which prevents the further movement of the fire through the entire matrix itself. And you can have added aromatic content, or you might also add what is called halogen atoms like fluorine, chlorine, bromine, and iodine. Most of the time it is bromine, but what happens is that the halogens will combine with hydrogen and create a dense gas that will smother the flame, but that gas can be hazardous and not good for people around the composite system. You can also add fillers like magnesium chloride, or you can also add what is called ammoniated magnesium chloride or calcium bromide, or you can also add red phosphorus. And there is only one type of red phosphorus that is good for fire resistance, so you may add that to the matrix itself to improve the fire resistance. So the current trend is to add what is called alumina trihydrate, or it's also called hydrated alumina. And this ATH, that's what it is called. It has got 3 water molecules loosely bound, and it releases the water, cools and smothers the flame. It is relatively inexpensive, but sometimes when you add that, it increases the viscosity of the matrix resin, so it increases the problems with processing, but it is a good way to do that. So, you can have it as a coating rather than adding it to the entire composite system. The other properties that we are interested in is electrical properties of composites. And because this is especially important in electronics industry. So, you want to have dielectric properties, or you want to have some kind of a specific property, and that's because you want to use them as the um, board for creating electronic substrates. And if you are going to do that circuit boards, you want to have reasonably good electrical properties. Or even if you are using it in a aircraft structure, which is going to be, it has to be resistant towards lightning strike, and it has to have good electromagnetic interference properties. And this is especially important because almost all the polymers are non-conductive. They have extremely high electrical resistance and dielectric strength. And you want to reduce that if you have to use them in areas where specific properties like that are required. And so what happens is that you might want to have conductive fillers, or you want to have a conductive surface mesh made out of copper. So, but the problem with the copper mesh is that a composite, especially in an aircraft type of structure, they get struck by lightning. In fact, they say that every aircraft structure can get hit by lightning maybe once to twice during flight every day. And as soon as it gets struck by lightning once, it damages the surface properties. And that will have to be repaired by bringing the structure back, bringing the aircraft back into your repair place, and doing that and putting it back, which means you have to remove the entire area and you have to replace the entire conductive surface mesh. So those kinds of properties are required. So these things are extremely important. You don't actually think twice about it when you have a metallic structure in an aircraft type of an application. But in a composite, you have to think about it all the time. You also have to have UV resistance and optical properties. Why UV resistance? Because some of these composites are going to be exposed to sunlight and UV radiation constantly. And you do not want the bonding between the matrix molecules damaged by UV light. And typically the interaction between UV and the electrons inside the matrix are pretty strong, and therefore the UV light can degrade polymers. So which means that the strength of your composite system can go down over a period of time, which is exactly what you will find. Say if you let out your kids' toys in the in your yard, they would break down over a period of time if it has been exposed to sunlight for a very long time. So you have to have UV inhibitors like carbon black and things like that to improve the resistance to UV radiation. Composites also need to have good toughness, especially good interlaminar toughness. And this toughness is dependent both on the matrix and the reinforcement. So which means that they have to have the ability to absorb impact energy, and they have to be able to quickly diffuse that energy. And because what happens is that as a result of that impact, it can result in some kind of a delamination, which is not visible to the naked eye. And that means that this composite structure, after a low velocity impact, for example, if you have an aircraft structure and you have, say for example, it has landed and it is parked near the gate, at the gate, and you have an a baggage loading ramp that comes in at a very slow speed and bangs against the structure. What happens because of this low velocity impact? It results in some kind of a delamination. Even a simple drop of a hammer during repair by a technician can result in delamination type of failure, which is not visible to the naked eye. And that can result in lower fatigue resistance for your composite structure. And you have to have a good toughness for your matrix so that it can prevent this kind of a delamination failure. So there are multiple ways to do that. Depending upon the available time, we will address it if possible towards the end of this class. Not this class, towards the end of this course. So, what is the role of the fiber and the matrix on toughness? And why does delamination happen? It's because most of the time the matrix as well as the fibers do not have the same kind of ability to withstand elongation when a force is applied. So you have to use a polymer that has a flexible backbone, and these aliphatic polymers, they do not always have extremely good toughness, but aliphatic polymers are tougher than aromatic polymers. So in order to get good toughness, you have to add what are called toughening agents. Sometimes, and these can also have different kinds of materials that you add to get other properties. So some of these toughening materials are thermoplastic in nature, or you might add some kind of a rubber particles to toughen the material. But sometimes what happens is that if you add this material and what material is resulting from this, you get better toughness, but then it suddenly becomes susceptible to attack by chemicals and UV radiation. So, and it also reduces the thermal stability. It also reduces the mechanical properties of your composite. So there is a balance between the two types of properties that you are going to get from this kind of a system. So you have to worry about all these things in order to get good mechanical properties and good other properties like delamination properties and things like that. The other issue that might happen is that if you add these kinds of particles, they may not exactly improve the bonding between the matrix and the fibers, which means that it increases the permeability of gases through this system. So you end up getting better toughness, but you end up getting bad barrier properties. And that is also because if you are going to be adding thermoplastics, they have little or no crosslinks, but they do not have good barrier properties. So the best method to avoid this kind of an issue is to increase the toughness without compromising other properties. And what I also want to bring up is what is the standard method to measure these interlaminar fracture toughness of composites? It is by a technique called V-notch. You apply a V-notch kind of a thing, and then you do a bend test or a 4-point bend test or a 3-point bend test, and you see the reduction in properties, and there are equations to measure the toughness of your composite system from these properties. So let me stop here.